Hey there, Mr. Sutton here, bringing you the AB Calculus 2-6 Extra Practice Number 2 solutions on continuity. For this problem, we have this function defined by the piecewise above. We want to know which statement here is true, so we're talking about whether the function is continuous at x equals 1 or not continuous, and why would it not be continuous. So let's just start by trying to prove continuity. We'll start with the left and the right side limits. So the left side limit as x approaches 1, that's going to be using this first rule with x less than 1. So 3 to the 1 is going to be 3. Next, for the right side limit at 1, we're using this bottom rule because this is the x greater than 1 rule. So plugging 1 into all of these, we have, let's see, 1/2 times 1 squared is just 1/2. Minus 1 is negative 1/2. Negative half plus 7/2 is 6/2. That reduces to 3. When all is said and done. Now let's check out f of 1, because the function value is also important for continuity. So taking a look here, there's no rule for what to do when x equals exactly 1. We have this less than 1 rule, we have this greater than 1 rule, but nothing for 1 itself. So that is non-defined, doesn't exist, which means since f of 1 does not exist, the function itself cannot be continuous, at least at x equals 1. So this would be, let's see, choice B, not continuous because f of 1 does not exist. On this problem, we want to know which of these intervals describes a continuous interval for the graph of f above. So I just did this one by figuring out where the discontinuities were and doing process of elimination for each discontinuity. So I see we have a discontinuity at 1/2. That's an infinite discontinuity, a vertical asymptote. So that's going to rule out anything that has 1/2 inside the interval. For example, choice A can't be it. Next, I notice that we have a hole, a removable discontinuity at 3/2. That rules out the interval from 1 to 2, so choice B is gone. We next have a discontinuity at 5/2. This is a jump. That's going to rule out the interval from 2 to 3, so choice C is gone. And that just leaves us with choice D. Just looking at the graph here, we see that there are no breaks in here. There's this cusp, but that's not going to affect continuity. So choice D it is. For this problem, they're telling us the function f has a removable discontinuity at x equals 3. Which of these could be the graph of f? So let's just point out some of the key features for each of these graphs. So choice A, we have a removable discontinuity at 3, which is exactly what they said. So choice A is looking pretty good, but let's just consider the other ones. It won't hurt anything. Choice B has a cusp at 3, which doesn't really have any bearing on continuity at all. Choice C has a jump at 3, not a removable discontinuity. And choice D has a vertical asymptote, an infinite discontinuity at 3. So then out of them, choice A is the best answer. On this problem, we're told that the limit as x approaches 6 of a function exists and is less than 8, and that the function itself has a value of 12 at the x value 6. So which of these statements must be false based off of that information? All right, well, one key thing here is that this limit exists. So what does that tell us? It tells us that the left side limit and the right side limit at x equals 6 are going to have to be the same thing. So that means since the left and right limit have to match, choice C, which says that they match, and that has to be a true statement. That's guaranteed to be true. That's not just it could be true. This is guaranteed. So it definitely can't be false. So that means we can eliminate choice C because it can't be false. All right. What else did they tell us? They told us the limit at 6 was a number that was less than 8. So it exists, and it's less than 8. So it can't be negative infinity if it exists. It's a constant that's less than 8. Because of that, because we have to have some number that's less than 8, that means that the left side limit here actually could be 0. So this is definitely possibly true. It doesn't have to be true, but they were asking which statement had to be false. Well, because this could be true, it doesn't have to be false. And choice B is saying exactly this, really, that the right side limit is less than 8. Well, that's actually guaranteed to be true. If the overall limit's less than 8 and the limit exists, that means both sided limits are going to be less than 8. So this eliminates choices A and B together, which means it has to be choice D that has to be false. But if you're wondering how can we prove that this can't be continuous, Well, continuity requires the limit to exist. It requires the function to exist, which the function does because f of 6 equals 12. But continuity also requires that the function value and the limit be the same number. Well, here's the trouble with this. If your f of 6 is 12, that's a number that's bigger than 8. That means that whatever the limit is as x approaches 6, because it has to be less than 8, it can't possibly equal 12. So that means that our limit and our function value have a mismatch, so we're guaranteed that our function is not continuous at x equals 6. So then choice D, because that is the only false statement that has to be false. For this problem, I'm given this polynomial function, and I want to figure out for how many positive values of b does the limit as x approaches b of this thing equal 6. Well, the key on this one, because this is kind of weird wording here, the key on this one is recognizing that since this is a polynomial, which means that it is continuous, since we have a continuous function, asking where the limit of this thing equals 6 is the exact same as asking where does the function value of this thing equal 6. So since the limit and the function value are the same exact thing, I'm just asking where f of b equals 6. For what b value, which is really to say for what x value does this take on a value of 6. To figure that out, I'm just going to graph this polynomial and the line y equals 6 on my graphing calculator and see where they intersect, how many places they intersect. So let me go ahead and do that. So here I am in the y equals. I've put my polynomial function in y1. Here's my horizontal line, y equals 6 in y2. And not sure what the window should be, so let me go zoom 6. That gives me 10 units in every direction. And hopefully that's enough to see what I need to see here. So there's the polynomial, there's the horizontal line. And you might be wondering, well, since we don't know what window to use, how do we know this polynomial does not, for example, come back down and then go back up or whatever? So this is an even fourth degree polynomial. So just if you've graphed enough of these things, you know that this is going to have the end behavior of basically a parabola facing up. So this branch here, those are most likely going to be the going up forever branches of your parabola, and then you have a couple turns and twists in the middle here. But once you get to these spots here, you're pretty much going up forever. So here's my graph. In terms of what we need to figure out, again, we're asking how many positive values does our function equal 6 for. So intersections, we count 1, 2, possibly 3, and then 4. We're only concerned with the ones to the right of the y-axis, though, because they ask for positive values of b, so we can disregard this crossing over here on the left. But we still need to figure out how many times we're crossing at this little turnaround spot. It kind of looks like it's just touching once, but it's kind of hard to tell because we're not zoomed in enough. So let me go back to my grapher, and I am going to zoom in at this point. And let's see here. Let me go Z-box, and then where's my cursor? There's my spider. All right, so I'm going to open up a little box near this intersection point and press enter and just zoom in on that part of the graph. It's kind of neat. Extreme close-up. So zooming in, what can I see? Not a whole lot. Even zoomed in, it's kind of ambiguous. But that's okay. I'm going to zoom in again. Nothing to stop me, right? So let me get closer still, really close, and open another box. I can do this all day. All right, so we are really zoomed in at this point. I can't recall ever having to zoom in this much, but I'm glad I did, because look what happened there. And I'll just display something like that over here. So it turns out if you zoom in enough, your line is actually crossing the polynomial not once but twice at this spot. Okay, well, that's important. So we've got 1, 2 crossings there, another crossing all the way out here. That's going to be 3 positive values of b altogether, allowing us to choose answer choice C. On this one, we're given a table with some values of a continuous function f. Based on the data, we want to know what's the best approximation for limit as x approaches 4 of this function. All right, well, let's look at left versus right. As we come at 4 from the left side, starting at 3.9 and getting closer and closer, we look to be approaching the y value 7. And then as we come at 4 from the right side, we appear to be approaching the y value 7 as well, maybe, although it looks like we're approaching a little bit quicker from the right side than we are from the left side. But hey, who's keeping track? Still approaching 7. And they're asking for an approximation. There isn't like a 7.01 anywhere. So our two-sided limit then, just approximating it, got to be 7. Now, this is really the only realistic option if you're going to pick a number. 0 and 4 have nothing to do with the problem, really. But you might be tempted by answer choice D, no approximation because the limit does not exist. We can actually eliminate this one right off the bat, though. They told us that f was continuous. A function that is continuous is guaranteed to have a limit that exists. So therefore, we're going to have to go with answer choice C. On this problem, we're given this rational function with some absolute value fun thrown in. We want to know on which of these intervals is the function continuous. Well, probably the easiest way to do this is to figure out where it's not continuous and then eliminate the intervals that have those discontinuities. So taking a look, things that would make this not continuous are mostly going to be things that make the denominator 0. We do have this absolute value weirdness going on, so that might give us some kind of jump. If we did have a jump, it's going to be at the x values positive or negative radical 2. But those are the same x values that would also make this x squared minus 2 undefined. So we've got plus or minus root 2 is going to make our function unhappy. And also because of this other parentheses, negative 0.4 is also going to be an issue, also going to give us some kind of discontinuity. And it looks like it's going to be a whole. The other one, who knows, because we got the absolute value there. But in any case, we've got issues at these x values. All right, looking through all of these, answer choice A, the interval from negative 2 to negative 1, that contains negative radical 2. Negative root 2 is somewhere between negative 1 and negative 2. So that means we can eliminate answer choice A because it has a discontinuity. Choice B, negative 1 to 0, well, that has negative 0.4 in it, so choice B can't work. Choice C, 0 to 1, that doesn't have any of these values in it, so C is looking pretty good so far. And then choice D, 1 to 2, well, that contains positive root 2, so there's an issue. So by process of elimination, choice C. On this free response problem, we're given this f function here, this rational function that has not 1, not 2, but 3 mystery constants that we're going to have to find at some point. And we're told the graph of f has a vertical asymptote at x equals 1 and a removable discontinuity at x equals negative 2. Based off all this, we want to show that a equals 2 and b equals negative 4. So they're already giving this to us, but they want us to go back and prove it. All right, well, we're going to have to use the fact that we have a vertical asymptote at 1 and a removable discontinuity at 2. So what I'm basically going to do is just solve for a and b using this information, and then hopefully what I solve for happens to be 2 and negative 4. So let's start by using the fact that we have a vertical asymptote at x equals 1. Well, if that's the case, that means that when I plug 1 in for x, it's going to make my denominator 0. So I can say 2 times 1 squared plus a times 1 plus b equals 0. Again, this is because 1 is a vertical asymptote. So from this I can write 2 plus a plus b equals 0, which isn't really all that helpful just yet, but at least gives us one equation of information we can use. Now the other information we had is we had a removable discontinuity at x equals negative 2. Well, this means if I plug negative 2 into the denominator, that should also come out to 0. So 2 times negative 2 squared plus a times negative 2 plus b has to equal 0. So let's see here. This is going to be 8 minus 2a plus b equals 0. And now that I've got another equation, I can start using some of my system of equations solving methods to figure out a and b. One thing that would be pretty easy to do here is just isolate b. So let me just subtract 8 and add 2a to the other side. So b then is equivalent to 2a minus 8. And then I've got another equation here with a b in it. Let me replace this b with 2a minus 8. So I'm just going to rewrite this down here. So I'm going to write this as 2 plus a plus 2a minus 8. So this is going to be, let's see here, negative 6 and 3a, which means if I add 6 and divide by 3, a must equal 2. And now I can go back to this equation. Well, if a equals 2, then b must be 2 times 2 minus 8. So b must have a value of 4 minus 8, which is negative 4. And so we've proven what we set out to prove, which is that a is 2 and b is negative 4. On part B of this problem, ironically, they're asking us to find c, because we already found a and b in part 1. So in order to find c, we're again going to use the fact that we have a removable discontinuity at x equals negative 2. If this is the case, then not only should the denominator be 0, which we used in part A to find a and b, but we should also have a numerator that comes out to 0 when we plug in negative 2. Because a removable discontinuity, when you plug it in, you get 0 over 0. So let's plug negative 2 into the numerator here. So using this removable discontinuity, we can write c times negative 2 minus 5 times negative 2 squared. So this is negative 2c minus 20 equals 0. So adding 20, dividing by negative 2, we come up with a c value of negative 10. For this problem, they're saying to make f continuous at x equals negative 2, f of negative 2 should be defined at what value? Okay, so to move any further here, we need to rewrite this with a, b, and c actually plugged in. We need some numbers at this point. So plugging in what we found, which we saw that a was 2, b was negative 4, c was negative 10. This is negative 10x minus 5x squared over 2x squared plus 2x minus 4. All right, now that we're working with that, what should we say that f of negative 2 is to make this thing work out? Now, the reason they're asking this problem in the first place is if you just try plugging negative 2 into this thing the way it is, you're going to get 0 over 0, which we already know before we try it, because they said we have a removable discontinuity at x equals negative 2. So they basically want us to remove that discontinuity and come up with a value that this thing should equal. And maybe they're thinking of making a piecewise function where this is what we write down if x does not equal negative 2, but if x does equal negative 2, then we have some other value that this equals. But we don't want it to just be any old value. We want it to be a value that makes this thing continuous. So that means that whatever value this thing equals when we plug in negative 2, it needs to be the same value that we get when we take the limit of this as x approaches negative 2. So let's go ahead and find that limit. Now, to find the limit, we already know that plugging in negative 2 over 2 is not going to get us anywhere. So we need to first factor and cancel out. My numerator, I can factor out a negative 5x. That would leave me with 2 plus x. And in the denominator, I can at the very least take out a 2. So that's going to be x squared plus x minus 2 left over. And then doing a little more factoring, things that multiply to negative 2 and add up to positive 1. That would be x minus 1 and x plus 2. And then we can definitely cancel out those x plus 2's. So this is negative 5x over 2 parentheses x minus 1. Notice that I still have the limit as x approaches negative 2 sticking around here because I have not actually evaluated the limit yet. I'm just rearranging things. But now that I've canceled out the problem child here, I can plug in negative 2, and I don't need the limit anymore after I do that. So I've got negative 5 times negative 2 over 2 times negative 2 minus 1. And if you wanted to simplify it, which you don't have to, but you could, this is going to be 10 over, let's see, this is 2 times negative 3, so negative 6. So that ends up reducing, if you wanted, to negative 5/3. For this last problem part, they want an equation for the horizontal asymptote for the graph of f. So again, here is the graph of f with a, b, and c plugged into it, and we saw this on part C. So now if I want the horizontal asymptote for this, since this is a rational function, it's only going to have one horizontal asymptote, which I can find by taking the limit of this thing either as x approaches positive or negative infinity. To make my life easier, I'm going to take the limit to positive infinity. So to do that, I'm just going to choose my champion, use the dominant terms on each side of the fraction. In the numerator, this negative 5x squared is the fastest growing function. And in the denominator, it's this 2x squared. So just reducing that, we get negative 5 over 2. So they wanted me to actually write an equation here. So let me write y equals negative 5 halves for my horizontal asymptote.